Hello everyone, I am Pratik Prajapati, a PhD student working at Human Centered Robotics Lab, Indian Institute of Technology, Gandhinagar, India. This video is regarding the presentation of paper selected at the International Conference on Robotics and Automation ICRA 2020. The title of the paper is On the Human Control of Multiple Quadcopters with a Cable Suspended Payload System. The main motivation of our work is to aerial transportation of cable suspended payload using multiple quadcopters by a human operator. The payload can be transported by fixed attaching to the chassis as done in pizza delivery drone, or mechanical arms or gripper can be attached that can pick the payload. Another way is by using the cable that suspend the payload as seen from this picture. A company named Aeron conducted the experiment to transport a human from one place to another, in which human hangs using cable from the helicopter. Suspending the payload using the cable has mainly two advantages. One, the agility of the quadcopter retains as the attitude dynamics of the quadcopter will not be affected by the payload dynamics. Another advantage is the payload can be picked up from the certain height. Now further I would like to show a video of harvesting the Christmas tree using the helicopter. Here you can see that pilot is highly skilled to counter the payload oscillations and pick and place of the Christmas tree at the particular location. So one question could be arise that can we come up with some control scheme in which helicopter itself controls payload oscillations and pilot need not to worry about the payload oscillations. Moreover, single quadcopter has low payload carrying capacity. One of the solutions to this issue is the use of multiple quadcopters collaboratively transport the payload. Let me show you another small video. In this video, a swarm of ants work together and share the load among each other to transport the stuff. Thus, based on this observation, the motivation of the present work to come up with the control strategy for human flying of multiple quadcopters with a cable suspended payload that can counter the payload oscillations, and human operator need not to worry about the reducing the payload oscillation explicitly. Consider a system of having n quadcopters with cable suspended payload. The initial frame of reference is represented as a frame I, and the body frame of payload is denoted as a frame B. The vector rho represents the position vector of a cable attachment point on the payload from payload center of gravity. The configuration space of the system is given as the position of the payload x0 in R3, its attitude R0 in spatial orthogonal group SO3, attitude of ith cable Qi in spherical group S2, and attitude of ith quadcopter Ri in SO3. The control input to the system is thrust force Fi and moments Mi generated by the ith quadcopter. Consider the case of two quadcopters transporting a cable suspended payload. As a human cannot control two quadcopters simultaneously, a leader-follower strategy is adopted, in which human controls one of the quadcopter denoted as leader quadcopter, and other quadcopter is the follower that is autonomously controlled to facilitate a stable flight. Commercially available quadcopters are equipped with onboard PID attitude controller. Hence, human operator need to provide the desired roll, pitch, and yaw rate along with the thrust force to control the motion of the quadcopter. Now to assist the stable human flight of such system, in this work, to control the motion of the follower quadcopter, payload attitude controller PAC, which takes the feedback of payload attitude and its rate to control the payload oscillations, and a cable attitude controller CAC, which takes the feedback of the cable attitude and its rate to control the cable oscillations, is designed. Thus, CAC and PAC will facilitate human operator to fly a multiple quadcopter system. The thrust force generated by ith quadcopter is acting along the third body fixed axis. However, initially to define the controller, the components of the thrust force along the inertial axis is considered as the fictitious control input UI without considering the rotational dynamics of the quadcopter. For a stable transportation, the cable should be in the vertical direction and payload should remain in the horizontal plane, and corresponding angular velocities of the cable and payload should be zero. Thus, the system dynamics are linearized above the hover equilibrium configuration, and it is given by these equations, where eta 0 represents the variation in the payload attitude and zeta represent the variation in the cable attitude. The linearized model can be written in the state space form as given by this equation. A state feedback controller is developed. As control input to leader quadcopter is delta U1 is taken as minus kh into z, where kh is the human feedback gain matrix. For the follower quadcopter, CAC and PAC are written using these equations. KIPAC and KICAC are the feedback gain matrices for PAC and CAC. The system stability can be achieved by making A0 minus B0 K matrix to be Hurwitz. Thus, for stable transportation, the follower quadcopter need to generate the desired thrust force UD. The thrust force generated by the quadcopter acts along the third body fixed axis. Thus, by orienting the quadcopter at a desired attitude, the desired thrust force UD can be achieved. The desired attitude of the quadcopter can be found out by comparing the linearized translation dynamics of the quadcopter with the fictitious control input UID. The desired yaw angle can be chosen arbitrarily as it is decoupled with the roll and pitch angles for linearized model. Finally, a PID attitude controller is used to track the desired attitude of the quadcopter using this equation. To validate the control strategy, experiments of the two quadcopter with cable suspended payload was conducted. A small scaled quadcopter with MDF strip as a payload was used for conducting the experiment. To estimate the cable and payload attitude and its rate in real time, Vicon motion capture system was used. Human operator was asked to follow a 2 meter cross 2 meter square trajectory in the horizontal plane. Human provides input in terms of desired roll, pitch angles and thrust force to leader quadcopter to direct the system along the course using RC remote controller. The control algorithm CAC and PAC was written using robot operating system. CAC and PAC calculates the desired commands for follower quadcopter that control the oscillations of the cable and payload, making the stable human flight. This video shows the experiments conducted for the two quadcopter with cable suspended payload. Quadcopter 1 is considered as a leader quadcopter and quadcopter 2 is considered as a follower quadcopter. Initially, the system was flown without implementing the cable attitude controller CAC and payload attitude controller PAC. As we can see in the video, the master quadcopter flew as per the human commands, but the follower quadcopter had no appropriate commands. It just hovered for some time and the entire system crashed. Now the system was flown using PAC and CAC. The human operator was asked to fly the system in 2 meter cross 2 meter square trajectory in horizontal plane. As the CAC and PAC is implemented, the leader quadcopter directed the entire system as per the human commands, and the follower quadcopter stabilized the entire system by reducing the payload and cable oscillations. The decay in the cable attitude and payload attitude can be seen from these plots. The simulation for 3 quadcopters with the cable suspended payload is carried out in MATLAB numerical environment. Here the leader quadcopter were given the specified roll and pitch angles with the thrust force that can follow the square trajectory in the horizontal plane. Other two follower quadcopters take care of the payload and cable oscillations, which stabilize the entire system. We address the problem of manual control of multiple quadcopter systems, collaboratively transporting a cable suspended payload. Proposed CAC and PAC successfully demonstrate to enable stable human flight of two quadcopters with cable suspended payload and can be extended for n number of quadcopters. In future work, the experiments for more than 2 quadcopters will be conducted. In this work, cable and payload attitude and its rate were measured using the motion capture system that restrict to conduct the outdoor experiment. However, onboard sensors will be designed that can accurately measure the cable and payload attitude to allow the outdoor experiments. Some potential applications in the agriculture, warehouse, and impromptu transportation of the payload will be considered in the future. Thank you.